So Dani received a PhD from the University of Michigan with Professor John Wolfe, and then did a postdoc at the University of Wisconsin-Madison with Professor Teshik Yoon. Dani joined Merck in 2014 as a member of the Process Chemistry and Enabling Technologies Group, and this year she became the Director of Discovery Process Chemistry Group in Kenilworth, New Jersey. Throughout Dani's time at Merck, she's been involved in developing synthetic routes for drug candidates spanning HIV and oncology, and also using HT and photochemistry to address synthetic challenges across pharmaceutical development. So over to you, Dani.
Thank you very much. Okay, so folks can see this, looks good. Okay, thank you. Yeah, so thank you very much for the invitation today. I'm really excited to be here to talk about some of the challenges that I have overcome in catalysis, both internally and also externally, with the common thread being collaborations is a way to overcome all of that. A shameless plug is a pandemic hobby that kind of emerged, which is a podcast. And I encourage folks to check it out, where we highlight Merck stories that definitely, go into some of the challenges that we overcome on a day-to-day basis. So a little bit of background about process chemistry at Merck. We span actually from discovery chemistry all the way to late development, and our roles kind of changed throughout that time. Currently, I'm in a discovery process chemistry group, which kind of straddles this discovery slash early development line. And it's a really fun space where we use process chemistry mindset to help enable SAR and find really nice ways to do scale ups to enable the preclinical safety studies. But I think what is underpinning everything is just an excellence in synthetic chemistry. And before joining the Discovery Process Chemistry Group, I was a member of the Process Chemistry Catalysis Group, where our main mindset was, how are we going to make active pharmaceutical ingredients as efficiently as possible? And we always like to go from using a commodity chemical, something that is readily used from multiple industries, and in as few steps as possible, convert it into API. Ideally, this is one pot, no waste. That is sometimes really hard to achieve, but nonetheless, we kind of always try to hold ourselves to that standard. Obviously, this isn't done alone. And here I'm highlighting a lot of the different groups that kind of come into play across Merck as we undertake a manufacturing route development. Keep in mind that this isn't restricted to just small molecule typical targets. Our company also has a process chemistry mindset as we go into biologics and also vaccines. But for the focus of my talk today, it's mainly going to be on small molecules. So when we think about an ideal manufacturing route, as I mentioned before, taking commodity and going all the way to API in as few steps as possible. And there are some considerations that have to be taken into accordance, such as your process has to be sustainable, efficient, robust, inexpensive, safe, and also easy to operate. And when you think about how do you readily convert commodity all the way to API, I think this audience knows that catalysis is usually at the heart of that. And so naturally, all of these ideals that I have shown here become challenges in catalysis, where your catalysis has to be efficient, robust, inexpensive, using a base metal versus a transition, safe, sustainable, and so on. And so for the talk, for the rest of my talk today, I'm mainly going to be focusing on, a story that was internal, which was focused on developing a nucleophilic fluorination. And then I'm going to pivot in my last few minutes to highlight a paper that we recently published last year that kind of helps bridge the gap and address the challenges that exist between our external and also internal chemists as well. So Rhiannon did a really great job kind of teeing up my talk. One compound that we're really excited about at Merck is MK8591, also known as Islatravir. It's a really novel NRTTI used for the treatment of HIV. And what's really phenomenal about this compound is that just at a very low dose, such as 0.5 mg, it can suppress your viral load for up to 7 days and also beyond. And what this does is it really opens up the door to, new ways to thinking about HIV, new ways into thinking about HIV treatment, but also into prophylaxis. Now, the structure of MK8591 bears a lot of similarity to just deoxyadenosine. And naturally, what folks kind of, start to think about, especially at Merck, where we have a very robust biocatalysis and protein engineering team, is how can we leverage nature and specifically enzymes to potentially manufacture MK8591. And we thought that we could really take advantage of this nucleoside salvage pathway and run it in reverse, where your starting materials would be something that resembles a triol and also acetaldehyde. And then through a series of steps, you could eventually arrive at your API. Mind you, the key differences between MK8591 and also deoxyadenosine is this alkyne and then this floral group on the nucleobase. Again, as what was pointed out really well before, this works beautifully, and our teams came together and made this really elegant, fully biocatalytic cascade to arrive at MK8591. This is the manufacturing route that's put into place. So, hundreds of kilograms have been made using this route. And I think the unsung hero, or the untold story, if you will, in all of this is 2-fluoroadenine. Many times when I give this talk, folks are like, well, how do you make 2-fluoroadenine? And that's a really good question, because it's really, really hard. And when you think about 2-fluoroadenine and what our manufacturing principles are, going back to commodity building blocks is going to be paramount. And what maps on really nicely is adenine and also guanine. But there are challenges here when you think about taking either one of these to 2-fluoroadenine. The main challenges are that for fluorination, you need it to be mild and efficient and safe. The amination, we want it to be selective and as atom economical as possible, so likely using ammonia. And lastly, and something that is sometimes not thought about, is that 2-fluoroadenine comes in at the very last step to make the API. So if you have any derivative of 2-fluoroadenine, it's naturally going to become incorporated and be an impurity that you're going to have to reject. And so, as many folks like to say, challenges are actually opportunities. That is the case here as well. So let's kind of go blow by blow through these. Adenine, ideal. It only differs by one atom of fluorine. And I screened this reaction for about a year and a half, and despite my best efforts, I was unable to directly fluorinate adenine, and ultimately this approach had to be abandoned. But I think it really speaks to the need for developing really cheap and robust CH fluorination chemistries, and I hope folks on the line can maybe pick this up and pursue it. So what about guanine? Well, you can take guanine, which has an OH here, and in one step convert it to this fluoroguanine derivative. And we had a few options here. You could either aminate first, and this was demonstrated. However, we had some safety concerns with the fluorination step, where we were using terp-butyl nitrite in the presence of HF pyridine. And ultimately, while we were able to demonstrate this in flow and have a good process, we ultimately wanted something that was a little bit more robust. Okay, how about if we fluorinate first? Well, by adapting some aqueous Sandmeyer conditions, you could indeed fluorinate to make this chlorofluoropyrene. However, we saw around 30% loss of product because hydroxylated impurities due to using aqueous HBF4. However, what we did observe is amination. And amination at first was not as controlled as we would have liked. And so we saw ammonia was being incorporated both at C2 and also at C6 to make different derivatives. So we wondered, can you make C6, shown right here, more electrophilic so that amination is more selective? And how would we do that? Well, we wondered, what if we make the difluoropyrene shown here? Would this improve the selectivity? So with a bolus of this chlorofluoropyrene in hand, we were able to make this difluoro product by using a phase transfer catalyst in the presence of KF. And what we observed is within minutes, you very selectively aminate this in a pretty good yield, and then selectively remove the THP protecting group as well. Now, ideally, we would like to not go through the chloro-fluoro to then go to the difluoro. And so we wondered if we could take guanine, convert it to this dichloropurine, and maybe come up with a new halex reaction that is a little bit less extreme. We thought we could maybe even do this in one pot. And in doing so, we could circumvent HBF4 and have our one-step fluorination and also amination. And we thought that there were two different ways to kind of arrive at this. So two different approaches for accessing the 2,6-difluoropurine. One is we could, enhance the electrophile through purine activation. And we thought that if we had this dichloropurine and if we had a nucleophilic catalyst, it would basically displace the chlorines, make these high energy quaternary adducts, which then in the presence of a nice, cheap and inexpensive fluoride source, such as KF, you could arrive at the difluoro species and then aminate. Another approach that we thought about is if you can soup up the nucleophilicity of the fluoride, and this would likely be done through a catalyst. And there were several different types of catalysts that we could explore, such as phase transfer, H-bond donor, and also, using some sort of metal complexation. Ultimately, what we decided to, go with is, using the purine activation pathway. However, I'll end my talk with a little vignette that kind of explores the fluoride activation as well. So what we did is we went to running screens, and I was able to look at a variety of different tertiary amines that would serve as that nucleophilic catalyst in 4 different solvents. The size of the bubbles correspond to percent conversion, and the color corresponds to percent desired product. So you want to look for big green dots. If you see a big green dot, that's good. If you see a big red dot, that means full conversion, but not to what you wanted. And we saw a lot of really interesting results here, where Dabco and aqueous trimethylamine looked really promising. And when you think, though, what are the challenges that could come here? Well, one of the first ones that comes to mind is scale. People always question, does HTE scale? And so this is something that we were going to have to demonstrate. And also mixing. These reactions were done in 1 ml vials with a stir bar. These reactions are heterogeneous, and so you could think of making really fine KF particles, which could give you maybe an unrealistic yield boost in the instance that you'd have to switch to overhead stirring upon scale. And so we, our team quickly started to evaluate this approach on a 2 to 10 gram scale, and we were very delighted to see that indeed, trimethylamine was our best nucleophilic catalyst that we had seen, and we're getting around 82% of our desired difluoro product. And so just to summarize, trimethylamine and DMF was what we wanted to use going forward. So long story short, this reaction was very, very, I'm glossing over a lot of details, but we were able to, really find a really nice process here and actually do a direct isolation simply by adding water at the very end and make these really beautiful 2-fluoro adenine particles. Cindy Hong was the process chemist who co-led this effort, and there she is with her batch with a thumbs up. And so again, I just want to hammer home not only milligrams to grams, but we were also to demonstrate milligrams to kilograms. And so 220 kilo scale in this reaction performed beautifully. But to go back to kind of where I started, we did have some really interesting preliminary results with this fluoride activation route, and we wondered if this was going to be an opportunity to potentially improve the halex reaction. So halex refers to halogen exchange, and traditionally it's a metal-free type process, but it is really extreme, and your substrates have to be very reactive. And so because of this, it has very limited industrial applications. However, one way to kind of address the halex limitations is to make that really nucleophilic fluoride source. And TMAF, definitely has its advantages. It's soluble in most organic solvents, and it works really, really well at this. However, TMAF is incredibly hygroscopic and very, very expensive. And so for a benchtop chemist wanting to explore this chemistry, you'd almost have to be limited to a glove box. And so what we wondered is, can you generate TMAF in situ, specifically by using a tetramethyl ammonium salt in the presence of a phase transfer catalyst? And what we had observed in the fluorination of dichloropurine is that the first fluorination event happens really, really fast. So it happens at C6. However, the sluggish one is the fluoride introduction at C2. And so we wondered, could we, do a counter ion swap using either cesium fluoride or potassium fluoride with an ammonium salt to increase it? And would a PTC also kind of boost that fluoride, the fluoride solubility and nucleophilicity as well? So naturally, you have to go to a good screen. And this is one of the first screens that I ran. And as I alluded to before, we knew that the most challenging fluorination was going to happen at C2. And so that's the one that we kind of focused in on. So all my screens were based off of the chlorofluoro substrate, because we knew that this second fluorination was the one that we really needed to pin down. And so below, I'm showing either cesium fluoride, potassium fluoride with a variety of different PTCs and different ammonium chloride or tetramethylammonium salts. And what we observed is that indeed cooperative catalysis was observed. So these are the two controls without any sort of PTC present. And this was really exciting, because what we were seeing is that our best results were using 18 crown 6 in the presence of either tetramethyl ammonium chloride or tetramethyl ammonium PF6. Mind you, this is also all done in acetonitrile at right around 40 C. So just to kind of drill down our conditions, we were able to see that tetramethyl ammonium chloride was indeed the best counter ion with 10 mole% of 18 crown 6. Again, seeing really nice conversion to the difluoro adduct. And so the key takeaways here was that this is a really inexpensive cocktail to make. It's very atom economical, and there was no glove box required. But the substrate is pretty specialized, and so we always wondered, is this general? And I don't want to really go into a substrate scope, but we were able to see really nice translation of the conditions that we had adopted for making 2-fluoroadenine into a wide variety of different heterocycles as well, and also into aryl triplates. So a question that often comes up is, are you actually generating TMAF in situ? And for that, we relied upon our NMR group, where we did F19 studies to kind of hammer this down. And so the fluorine NMR for TMAF shows this triplet at around 148 ppm. And what we observed is that you can reconstitute that triplet in the presence of all three. So cesium fluoride, tetramethyl ammonium chloride, and also the PTC. And this work was published in JOC in 2021 with my two collaborators, Cindy and Aaron. And I would be remiss if I didn't also bring up, I am an alum of the University of Michigan, and Melanie and her team published a very elegant route to also addressing the TMAF problems, where she made these TMAF adducts that had these different alcohol groups appended to them. And what I loved is this really elegant kind of structure activity relationship that she had developed here. And what I really love about this story is that it was done in partnership with Corteva, which kind of gets to how I'm going to conclude my talk, is that pairing up with industry kind of helps you overcome a lot of your catalysis challenges, because it exposes you to things that a lot of the external community wonders about, which is, why don't you use my chemistry? I think that's a challenge that a lot of academics ask. And so, why don't you use my catalyst? Because it takes 15 steps to make. And if we're going to do any sort of manufacturing route development, we do not want a ligand that it takes more steps to access than the actual drug that we want to make. And so to kind of flush out our thoughts on this, my boss, Elsie Campo, and I wrote a comment in Nature Chemistry last year called Harder, Better, Faster. And here we basically, it's a call to action that if we really want to advance, synthetic organic chemistry, we need to roll up our sleeves, and we need to start to have kind of these uncomfortable discussions at times to kind of, ask ourselves, will my chemistry ever be adopted? And, what are your thoughts on how to make it better? For me, I'm a huge fan of academic industrial collaborations, and I don't have time to get into the ones that I have been part of, but a few that I like to highlight are shown here. So with Deepanita Kalyani from St. Olaf, and now she's at Merck, and also Corinna Schindler, who's at Michigan. And what I think is a really beautiful way to kind of bridge the academic industrial gap is through HTE. It's almost like a gateway drug. Because folks have a lot of catalytic reactions that they're really interested in trying to optimize. And by teaching folks HTE, which I think is really readily accessible, they can kind of start to address a lot of their own challenges here. And so, for instance, with the collaboration with Deepa, we wanted to explore the scope. Specifically, her chemistry was very restricted to aryl bromides, and we thought aryl chlorides are much more readily available. And if we could have them include, pharma relevant scaffolds, that this would be more widely adopted. And indeed, this was the case. So with that, I would like to conclude, and hopefully there's still time. That's good, and open the door up to any questions that folks have.
That's great. Thanks very much, Dani, for an excellent talk. So yeah, as before, please type any questions in the Q&A box, and while those are coming, I will jump in with one. So in terms of engaging from an industrial perspective with academia, what have you found the biggest challenges to be, or kind of things that have helped to smooth some of those discussions initially?
Yeah, I think you need to be approachable, and maybe that is something that some do better than others. I guess the little things that I like to do to engage with academia is sending quick notes to folks who publish papers, right? Like whether it's on Twitter, whether it's an email just saying, hey, this is really great. Have you thought about this? Just to kind of get like the dialogue going. And that's pretty low barrier. And then with that, hopefully one day we'll go to like a conference that's in person, and again, going to people's talks and just sticking around towards the end and just asking questions. But I think people fear that, I feel like the academic community just fears that maybe industry isn't concerned with what they're working on, or that the process is just so complicated, and it really isn't as complicated as what folks think.
That's brilliant. Thank you. And so we've had a question come in from Mark Stradiotto saying, thank you for the great seminar. Can you comment on scaling or reproducibility issues such as particle size or residual salts associated with the use of cesium fluoride?
Yeah, so good call out, because definitely that was a lot of challenge when we started to go with potassium fluoride for the scale up chemistry, where particle size control became very critical, and to a point where there was only a select number of vendors that would supply the particle size that we needed. So in that instance, though, you don't necessarily want to be reliant upon one or two companies to give you that. And so we also explored milling our own material as well to get the particle size that we required.
That's great, thank you. I guess maybe if I can follow in from that one, then how often do you see cases whereby you suddenly realize that you need that specific particle size because you get one result when you're looking at it in HTE with the stir bar, and then you come to scale up? Is that something you see relatively commonly, or have you got a different way of assessing things before you even get to that point?
That's a really good question. I mean, we do have different lots. Now that we've gone through this exercise, we now, have a more holistic view to the, particle sizes of, different KF or cesium, salts. But one thing that's kind of come into play is, this program that we were working on was going to go into phase 3. And so we knew that likely, we needed to get this hammered down. And so what that means is that our procurement folks, the folks that help us secure the right types of vendors to supply what we needed, we basically have those conversations as early as possible so that we can bring on alternative folks as vendors in the instance that we aren't able to get that. But to your point, yeah, I don't know how you necessarily de-risk that. It's just something that you just kind of observe, I think, and then you just, leverage lessons learned and try to fix it as fast as possible.
That's great, thank you. And had another question in from Enrique Lozano saying, it's a bit of a different question here. Analytical tools for these reactions. At-line, online, or operando analysis?
Ooh, so we try to leverage as many online tools as possible. I believe for the 2-fluoroadenine study, I don't know if we had any online PAT tools that were leveraged for that, but that's something that we definitely try to take advantage of. Definitely as we have started to leverage more flow, that's a lot easier to kind of have this, in-process controls kind of built into place.
That's brilliant. Thank you. I don't think we've got any more open questions at this point. So just remains for me to say thanks again, Dani, for a great talk, and thank very much all of our speakers for this afternoon. It's been a great seminar. I've really enjoyed it.